In the last episode, we learned something fundamental. The brain communicates using electricity. Every thought, movement, or memory comes from tiny voltage changes inside neurons, but those signals are extremely weak, usually between 10 and 100 microvolts. To put that in perspective, that's millions of times smaller than the voltage in a household battery. And those signals don't just sit on the surface, they originate deep in the brain and must pass through brain tissue, fluid, skull, and skin. So the real question isn't whether the brain produces signals. The question here is, how do we measure them from outside the head safely and reliably? That question is where neuroscience meets engineering. The most common tool we use is EEG, which stands for electroencephalography. EEG does not read individual neurons. It cannot see single spikes or single cells. Instead, EEG measures voltage differences on the scalp that are created when large groups of neurons act together. Each electrode is a passive sensor. It does not send electricity into the brain. It only measures the electrical potential at one point on the scalp relative to another point. And this is important. EEG never measures absolute voltage. It always measures differences, and that's why every EEG system needs a reference electrode, a stable comparison point. What EEG captures is the combined electrical activity of millions of neurons firing in synchrony. Look, it's a population-level signal, not a microscopic one. To understand why EEG works this way, we need to look at how neurons generate signals. Individual neurons fire action potentials. They're fast, sharp spikes, but these spikes are brief and cancel out quickly in space. EEG is not driven by those spikes. Instead, EEG mainly reflects postsynaptic potentials, slower voltage changes that happen when neurons communicate with each other. When thousands of neurons receive input at the same time, their electrical field line up and reinforce one another. When that happens across large areas of the cortex, those small fields combine into a signal strong enough to detect at the scalp. This is why EEG captures rhythm and timing, not precise location or single-cell activity. It tells us when large populations of neurons are active together, not exactly which neurons fired. Not all neurons contribute equally to EEG. The strongest contributors are pyramidal neurons in the cerebral cortex. These neurons have a unique structure. They are tall and they are aligned in the same direction, perpendicular to the surface of the brain. And because of this alignment, when many pyramidal neurons activate together, their electrical currents add up instead of canceling out. And that alignment is very critical. It turns microscopic electrical activity into a large-scale electric field that can travel through the skull and reach the scalp. By the time it gets there, the signal is weak, only a few microvolts. But with sensitive electronics, it becomes measurable. And from here, electrodes, amplifiers, and digitization will take over. Once the electrical field reaches the scalp, the electrode becomes the interface between biology and electronics. An EEG electrode is a small conductive sensor, usually silver chloride or gold. Its job is simple: measure voltage at one point on the scalp relative to a reference point. The electrode does not pull current from the brain, it only senses potential. To do this accurately, the contact between the electrode and the skin matters. You have hair, dry skin, and air all resist electrical flow, and that resistance is called impedance. High impedance means poor signal quality. So what EEG systems use gel or saline to lower that impedance and stabilize the measurement. Good contact doesn't make the signal stronger, it actually makes it more faithful. Even with good electrodes, the signal is still tiny, far too small for a computer to read directly. So the next step is amplification. EEG systems use specialized instrumentation amplifiers that boost the signal by tens of thousands to millions of times. At the same time, they reject noise that appears equally on all electrodes, like interference from cables or the environment. This is called common mode rejection, and it's critical for clean recordings. After amplification, the signal is still analog, a continuous voltage changing in time. Then you have an analog to digital converter, or ADC, that samples that voltage at fixed intervals, typically 250, 500, or 1000 samples per second. At that moment, brain activity becomes data, a stream of numbers that software can analyze, and that's where the magic starts. The first time you see raw EEG, it doesn't look like thought. It looks messy, unstable, and even unpredictable. That's because EEG records everything electrical near the head, not just neural activity. When you blink, the muscles around the eyes generate large voltage changes. When you clench your jaw, the muscle fibers produce high-frequency electrical bursts. Even the heartbeats would create a subtle rhythm in the signal. These are called artifacts, signals that are real but not neural. They overlap with the brain activity in both time and amplitude. So before we can interpret EEG, we must separate brain signals from everything else. The first step is filtering. Brain rhythms mostly live within specific frequency ranges. A high-pass filter removes slow drifts caused by movement, sweat, or electrode instability. You also have a low-pass filter, which removes fast activity, mostly coming from muscles. Together, these filters isolate the range where cortical rhythms dominate, usually between 1 and 40 Hz. We also apply a notch filter at 50 or 60 Hz, which remove interference from electrical power lines. Filtering doesn't invent information, it removes what doesn't belong. What remains is still complex, but now the structure starts to appear. Because EEG measure voltage differences, the choice of reference matters. Using a single reference electrode emphasizes local differences. Using an average reference distributes voltage across the entire scalp. Neither is universally correct. Each reshapes the signal in a different way. Reference choice affects amplitude, spatial patterns, and how activity appears across the head. After referencing, engineers evaluate signal quality. They check signal-to-noise ratio, spectral consistency, and relationships between regions. Only then the data can be trusted. This step is not optional. It determines whether EEG reflects the brain or measurement error. Once cleaned and validated, EEG reveals something remarkable. Rhythms emerge. Alpha waves during rest, beta activity with movement and attention, slower rhythms with fatigue or cognitive load. These patterns are not random. They are repeatable, measurable, and meaningful. Every waveform represents the synchronized activity of millions of neurons captured non-invasively and translated into data. This is the foundation of brain-machine interfaces. We've learned how to listen to the brain. The next step is learning how to decode. How do we decode how these rhythms become intent, commands, and control? If you get a value from this video, give it a thumbs up, subscribe to the channel. Take care, everybody. Bye-bye, bye-bye.